Hello everyone, my name is David Ecarone and I'm a PhD student in the Enhanced Regenerative Medicine Lab at the Italian Institute of Technology, Italy. The lab research focuses on biohybrid approaches for brain regeneration and repair, with particular emphasis on mesial temporal lobe epilepsy. Today, I will present my work on a biohybrid strategy to restore the hippocampal loop and control limbic seizure via closed-loop stimulation. Mesial temporal lobe epilepsy is the most common epileptic syndrome in the adult population and also the most often refractory to antipileptic medical therapy. Closed-loop deep brain stimulation is the latest frontier treatment when medication fail to control seizures, holding promise as a less radical approach than surgical ablation of the epileptic focus and bringing new hope to those patients who are not eligible for it. Closed-loop deep brain stimulation delivers electrical pulses ad hoc informed by patient's ongoing brain activity. However, our incomplete understanding of the dynamical unfolding of epilepsy entails a trial-and-error approach to devising the stimulation policy. As a result, DBS suffers for incomplete and variable efficacy to date. In this scenario, our leading hypothesis is that interrectal discharges present the key to overcome the trial-and-error approach and devise effective patient-specific closed-loop DBS strategies. Previous experimental work based on rodent hippocampus cortex slices treated with compulsion drug for aminopyridine has demonstrated that the interictal pattern generated by the hippocampal subfield CA3 is antictogenic when the hippocampal loop is intact. However, the C3 antictogenic role is hindered when the hippocampal loop is disrupted by Schaffer collateral scat. A scenario recapitulates the hallmark of MTLM. Building upon this, we have addressed the possibility of artificially re-establishing the CA3 to cortex connection via an electronic bridge, so to restore the non-seizing state in the disrupted hippocampal loop. The bridge detects events generated by the CA3 and forwards them in real time to the subiculum in the form of current pulses, aimed at entering cortical networks through afferent stimulation. While the CA3 to cortex pathway is artificially re-established, the cortical input pathway is still intact, and this paradigm establishes a biohybrid loop. On the left, you see a schematic summary of our experimental setup, while on the right, you see a snippet of the bridge in action, showing cortical recruitment upon detection of an interictal event in the CA3. Ictal discharges recorded during the baseline were no longer observed during the bridge, and they emerged again upon bridge interruption, confirming that this disappearance was due to the action of the bridge. In this particular case, only short population bursts remained, which were evoked by the stimulation. Overall, the bridge virtually abolished ictal activity. We hypothesized that the CA3 adapts and responds to the impinging cortical input, acting as an adaptive biological neuromodulator, and that the bridge efficacy stems in relying this adaptive behavior back to the cortex. To address this phenomenon, we have analyzed the temporal statistics of the CA3-driven interictal events, dissecting interictal and ictal periods. We have found that the CA3 interictal activity accelerates upon CA3 entrainment by cortical ictal discharges, a behavior that is confirmed by the statistical parameters of the interictal event intervals. The CA3 bridge adaptation was particularly evident in this exceptional case, in which the bridge gradually, rather than immediately, abolished ictal activity. Specifically, the bridge turned ictal discharges into short evoked population bursts after approximately 15 minutes of stimulation. Analysis of the temporal statistics of the CA3-driven electrical pulses confirmed the accelerating pattern while activity was still being abated and destabilization upon ictal discharges disappearance. Taken together, these results indicate that the bridge fosters a process of dynamic adaptation within the hippocampal loop, leading to ictal discharge disappearance at steady state. In conclusion, we have demonstrated the feasibility and efficacy of electric bridge as well of an interictal-based grammar for DBS in epilepsy, providing the proof of concept of a new generation of implantable biomedical devices for epilepsy treatment, outclassing the current trial-and-error approach. I thank the European Union for having made this research possible, and I thank you all for the attention. Please reach me out for any questions and comments.